Okay, thanks for coming. My name is Ben Stopford. I work at Confluent Inc., which is the company behind Apache Kafka. So Kafka is like a distributed message broker, essentially, that gets used quite a lot in big data use cases. So we're going to be talking today about contemporary approaches to data at scale. So this talk isn't about Kafka. It kind of predates my working at Confluent. But so the ideas here are definitely my own, and not necessarily those of Confluent, although I think there's a line there which is probably, there's some confluence in it, no pun intended. So when we're talking about data technology, what we really tend to be trying to achieve is some sense of locality. And that's kind of a fairly abstract way of looking at it, but it just means really that we've got a bunch of data, it's spread around some media, it might be disk, it might be memory, and we want to get it into some shape that has a degree of locality so that we can do sequential addressing. And the reason we want to do that is that if we can address any kind of workload sequentially, we can take advantage of many of the layers that computers have to make our operations efficient. So obviously the caching, CPU has levels of caching, the page cache, disk buffer, etc. So if we're accessing data with a sequential workload, the computer has a chance of actually predicting what we're going to do next. It's a very, very simple idea. And that makes things very, very fast. So to take the extreme, which is a sort of standard magnetic hard drive, if we stream data sequentially, we'll get maybe 200 megabytes per second. That's a pretty standard throughput for a magnetic disk. If we try and address it at random, we'll get maybe 300 reads per second. So for a 100-byte row, that's about 7,000 times faster. So you probably get this, right? Because most people have some sort of intuition that disks are kind of slow. But the intuition is actually a little bit more fine-grained than that because it's that disks are slow if we ask them to do something that's effectively a random workload. Whereas if we ask them to do something that's sequential, they're really quick. And this property is ubiquitous. It's got nothing to do with disk per se. So an interesting fact is actually if you randomly address objects around your address space, like many garbage-collected languages tend to do, you'll actually get performance which is pretty much exactly the same as sequentially addressing a magnetic hard drive. So the intuition that RAM is always fast and disk is always slow is not a particularly good one. Much better to think about whether or not a workload is addressing data randomly or sequentially. So the point here is really just what we want to do is obviously we just want to make our workloads as sequential as possible. So let's just to examine this a little bit further, let's think about a rudimentary database. And a rudimentary database is nothing more than a file. So if we want to add data to our little database, we can just append it to the end of the file, and that will work really well because that's a sequential workload, right? It's a sequential write workload. So we'll get the throughput of our disk media. And if we want to read data efficiently, we can also scan, right? So we could do what is the equivalent of a table scan within a database. Or we could jump to a particular offset and we could scan from there. Both of those would be very efficient workloads because of the sequential access. So that's quite nice. Obviously, what we're trying to do is avoid scattergunning the file system while we're reading data or writing data. But both of those patterns would work quite well. So if we think about kind of writing trade-offs, just appending data to the end of a file has some limitations. So let's say we have some workload where we actually want to change a value within our database. If we just append it to the end of the file, we'll end up with an orphaned version. So that's kind of OK if we table scan the entire thing and duplicate on the way. That would be all right. And obviously, we keep our nice sequential write performance. But obviously, that means that we have to scan the whole thing. Alternatively, we could do what a traditional database would do, which is to update in place. And this kind of assumes that we've got fixed width fields like a traditional relational database would do. And that works very efficiently from a read and write perspective, but of course, we're going to end up scattergunning the file system as updates come in, because we can't just append them to the end of this nice file. But so these two patterns are quite important for understanding how storage engines work in different databases, both sort of old school and contemporary. So scanning the entire file is of some use for some workloads, but it's obviously relatively limited in terms of its sort of general applicability. The next thing we tend to want to do is support some form of lookup. So not unsurprisingly, we would do this with an index. So obviously lots of different types of index. This would be an example of a B tree. We might use a hash index. We might use a bitmap index. We might just use a set of values with pointers and in a sorted file. That would work equally well. It doesn't really matter. But the traditional way of doing this is to have some kind of index structure and have some kind of heap file underneath and have the values in your index with pointers associated with them that tell you where the underlying data is. So again, all fairly rudimentary stuff. So the problem with an index is that it provides an overarching order which is read optimized. So the reason we added this is so that we can get very quickly to the value Dave. But as soon as we add that index, if we had this nice append-only structure which leveraged sequential I/O, then we'd lose all the nice benefits of that, because as values, so if we update the value Dave, we can append it to the end of the file, and that will be very fast, but we're still going to have to jump to the position within the index where Dave lives to update the value to say that Dave's value has changed or has appeared for the first time. So we've gone out of this nice sequential workload, and we've gone back to scattergunning our file system or address-based, depending on what kind of type of database it is. So that's kind of a bit annoying. So there are this is kind of a fundamental problem for databases. So anyone who's used a database will be aware that if you add lots of indexes, your inserts start getting really slow. And it's for this reason. So there are actually a whole range of different approaches for making or for getting around this problem. And we're just going to talk about 3 of them. And those essentially are the 3 that sit at 3 extremes, I guess, of the spectrum. And there are some which I won't discuss, which sit in between. So the first one is really simple, right? This is like really intuitively kind of obvious. So what you do is you stick your random workload problem into RAM. So you put your index in RAM. And that's what many databases do, and it works very, very well under certain use cases. So my problem of random I/O is only stored in RAM. All of my data sits on disk, and I can append to the end of it. And effectively, I've kind of solved my problem. Well, I've solved my problem actually only in the context that I have enough RAM to fit all my indexes in. That's actually specifically what I've done. So it turns out that that's actually not always that beneficial for a number of other use cases. So one is kind of big data workloads. So if we think of a big data workload, the problem with a big data workload is that we're likely to get into a situation where we don't want to provision enough RAM for all of our indexes. We want something that's a bit more effectively disk efficient. So there's another way of kind of reframing this problem so that we can get more efficiency, which is quite interesting. So in this approach, what we do is we take our writes and we batch them up, and then we sort them, and then we write them out to a little index file. And typically, this little index file will actually just be a sorted array of effectively key value pairs. But it could be another form of index if we wanted it to be. It doesn't really matter. But the key point is that instead of having one heap file and one overarching index, what we have is a set of small index files, each of which is navigable in itself quickly, but we lack that overarching structure that we had in the previous example, where we just had one big index. So that's kind of an interesting idea. You might think that what does that gain? What have you gained from doing that? Well, certainly one of the problems with going from one big index to lots of little indexes is that when you need to look something up, instead of having to just go to the index, find the value, get the value out of the heap file, and off you go, you have to consult all of these files. And in physical implementations of this, the number of these files will actually get pretty large. It will get into the hundreds, if not thousands. So you sort of have to navigate all of these different files in order to read something. So intuitively, you might think that, well, what have I actually gained by doing that? Well, the answer to that problem is that what we've actually done is we've shifted the problem of random I/O on write to a problem of random I/O on read. So now, in this model, we can sequentially stream data to a media very quickly, because everything's sequential I/O. But we now got this, I now have to read a whole bunch of files effectively at random. And because we've shifted from the write concern to the read concern, we can use some clever tricks to optimize reads. So it turns out that reads are a lot easier to optimize than writes. That's basically the crux of it. So we can use things like, the most common approach here is a thing called a Bloom filter. Who's familiar with the Bloom filter? Ooh, good audience. That's a great start. Okay, cool. Well, for those of you, I won't go into too much detail, but it's a very simple probabilistic data structure. It sounds kind of complicated. You can write one pretty quickly, but it just allows you to answer the question in a very small amount with a very small memory overhead of whether the data that you want might be in one of these files. So this is kind of an interesting. So we've got another approach, which is effectively to push the problem of random writes to a problem of random reads so that we can optimize with a clever index structure and, of course, all of those levels of caching that we had before, the caching within the CPU, the caching on the disk, etc. And this thing is termed a log-structured merge tree. And it's the basis of many storage engines that sit particularly in the big data space. So if you've used HBase or Cassandra, LevelDB, RocksDB, etc., they all use this structure. And it's based of a collection of small immutable indexes, and it's always append only on disk. We still have that problem that we had with the original file, where we're going to end up with duplicates. So we end up with this sort of garbage collection process that runs in the background to deduplicate things. But that's actually okay because, again, that's sequential access. And it's only the random access that's going to really kill us from a performance perspective. And then the nice thing is, obviously, we can use sort of low memory tricks to improve the performance of our reads. So it's shifting a problem from random access from write to random access of read. Okay, so those are two approaches. Stick an index in RAM, and secondly, use something like a log structure merge tree, which is going to push us to a random read workload. The third approach is kind of completely different. And this is effectively just the brute force approach. So if we imagine that we have a workload where we actually need to get at all of the data, and the most common, or at least a large amount of the data, and the most common use case for this is some kind of aggregation. Okay, so you kind of have to visit it anyway. So if you asked a traditional database to do it, it's going to table scan. So the columnar approach is basically saying, well, I've got to do all this scanning anyway, so what can I do to optimize these scans to be the most efficient thing, the most efficient sort of, the most efficient strategy that I can get, whilst obviously removing the data that I need to get my result. So it's a very simple idea. This is a tabular form. You can do it in a polystructured form as well. But we take a row, A, B, and C, and we split it up into 3 different columns. So each of these would be individual files. So we have a file with all of column A, file with all of column B, and a file with all of column C. And the reason that's quite a good idea is that if we want to do an aggregation, we can literally only access those files which we need. And that's quite typical in sort of analytics workloads. So we've already reduced the amount of data that we need to remove from disk. So that's quite a nice idea. The thing that's really important with this approach is that we have to keep the same order in each one of these files. So it would be really nice to be able to sort each one of these individually, but that wouldn't work because we're actually using effectively the row ID to bind these things back together again. And the reason for that is that whenever a column in a database ever does any work, it is always doing a merge join. Because unless you had some strange use case where you literally only wanted to access one column, you're always going to be doing a join. So it's all about basically optimizing for the best efficiency you can within a brute force workload. And the other quite nice thing that comes out of this pattern is that columns have a tendency to compress really well. So, for example, if you had, let's say you had a column full of country codes, that's got really low entropy, right? So that's just going to compress beautifully, even with a sort of very low-cost compression mechanism. Alternatively, you might have just an incrementing ID, which would delta compress beautifully. So there's some really neat tricks that you can do on this kind of, with this kind of data to decrease the amount of I/O that you need to do within the storage engine. So those kind of like those are like three approaches to building storage engines. And so brute force, less I/O, by column, use compression. Always you need to hold them in row order. Unfortunately, it would be nice if you could sort them all, but it just doesn't work out to be efficient. And the reason is that you have to do merge joins via row ID. And then there's some other stuff like you can add predicates on to compress data, and you can do things to make these things very efficient. So, which of these approaches a technology uses is a useful tool to sort of work out which workload it's going to be good for. So Kafka, so this is the product that the company I work for builds and supports. So Kafka is actually very efficient from a disk perspective because it's a message queue and it doesn't have a lot of the overhead that you tend to get associated with sort of traditional messaging products which have to implement, let's say, JMS or AMQP or one of those standard protocols. So it's very much based on the idea of just scanning to an offset, reading some values, giving some data to someone, and then going away. So the user goes away, they come back again, they go back to the offset where they were last at, and they scan a little bit more. It's a very simple idea, but it's very, very efficient because it's all about sequential I/O. So many of the NoSQLs that you use, ReactMongo, pretty much actually a large proportion of them, will take this approach of effectively just a very simple approach of memory optimizing their indexes. And that works really well for general purpose workloads. Where it will always become problematic is when where these index-based structures start to overflow onto disk. So very fast for memory-centric workloads, not so good when the proportion of memory available is much lower when compared with the amount of data that you need to store. So that's kind of the ReactMongo, et cetera. The big data tools tend to take this LSM approach, so HBase, Cassandra, RocksDB, et cetera. And if you use these tools, the one thing that's very obvious about them is that they have very good scalability as the data set grows, and the VM size is relatively small. So that's why these storage engines suit big data workloads. Mongo actually now has one of these because it has a pluggable storage engine model, which is quite nice. And then any kind of columnar database, be it an old one like Sybase IQ or a sort of more contemporary one like or any of the Hadoop stack that uses Parquet, Impala, etc. They all use it. They'll all take this approach of chopping data into columns and compressing it effectively. So that was a bit on storage engines. Now we're going to talk about parallelism. So in any workload that sort of goes beyond the size of a single machine, you end up getting into some use of parallelism. And I'm not going to talk about this too much, but we're just going to talk about a couple of simple and salient points. So one of the common patterns, which is fairly well known, is obviously the idea of consistent hashing. Who's familiar with consistent hashing? Okay, so it's very similar to what you do inside a hash map, effectively. So it's simply to say that I can use a well-known hashing algorithm to get data specifically from the machine that it sits on because I know that it's been sharded by its primary key. And this is actually a wonderful pattern. I mean, if you've got a problem that happens to fit into this space, you have a wonderfully scalable solution. The downside is that it's relatively simplistic. You can only access data by key. But it does give you this very scalable pattern and this very scalable mechanism for getting into a sort of distributed, shared nothing architecture. The other pattern is kind of the opposite, and that's broadcast. So this is what most analytics engines will do. This is what Hadoop does. And that's very simply to run a process or run a query, analytics, etc., on a whole bunch of nodes at the same time. So you're exercising them all. And you return a result at the end. So that's the broadcast approach. So the interesting bit, or the bit to watch, is the middle ground between these two. So any sort of consistent hashing-based approach will give you very good scalability. Any broadcast method will allow you to exercise a large number of machines to solve a big problem. There are quite a lot of workloads which sort of sit somewhere in between, and probably the best example of this is secondary indexes in NoSQL stores. So many NoSQL stores, Mongo, Cassandra, HBase, if you use the add-on, will provide a secondary index function. And you might actually be asking for something that's relatively unique, right? So you might just be asking for, I don't know, users by their name, where their name is not the sharding key. In that kind of instance, then, you just need to be aware that you're obviously going to exercise all of the machines at the same time, and that's going to limit the scalability. So the two patterns work really well. We just have to be aware of this middle ground. So the final thing when we're talking about parallelism is replication. So actually, to build any single store that truly scales, you have to have both of these things. You can't do it just with sharding. And the reason you can't do it just with sharding is because of that broadcast problem. If you're broadcasting to all the machines, then you're exercising all the machines, and that won't scale from a concurrency perspective. So replication is your friend. Replication is actually used in many stores for other issues, for other reasons, for redundancy, etc. That's probably its most common use. But where it's really useful from a performance perspective is just simply for scaling out in a very simple way. So we used to do this back in the 90s with relational databases. You just have like a reporting replica. It's the same concept as you might do inside something like Mongo or Cassandra, just by having a readable replica. So the key point with replication is that they allow us a way to isolate load. They allow us to isolate load onto a bunch of subsets of our data store, and that gives us a different form of scale out to just using sharding. So in any store that needs to scale linearly, you're likely to want to have both of these operators to play with. And it provides redundancy too. So the problem with using replication is that it plays off against a consistency. And this kind of concept has been made fairly famous by the use of the CAP theorem. People familiar with the CAP theorem? Probably a fair few. So this very, very simple idea that if you have multiple replicas and those replicas can't talk to one another for a point in time, then on a particular point in time, then you're going to have a hard time trying to make them consistent. That's a very simple way of looking at it. Which brings us on to this idea of atomicity and ordering. So atomicity and ordering is a very expensive property in any database. So most relational databases dating back to the 1970s would have some form of isolation level like serializable, which basically says, I'm going to ensure that it looks like all actions on this database have been done within a single thread. And in reality, very few of them these days even implement that, or certainly it won't be their default. And the reason is that even on a single machine, it's too expensive, particularly in the days of multi-core processors. In a distributed world, it's even more of a penalty. So it becomes something that we end up giving up, which actually, as a slight aside, is something I think is a bit of a shame in the current NoSQL world, because there's actually many ways that you can get better consistency concerns or better consistency guarantees that most of those products provide. But that's really a different talk. So one of the best ways to solve a consistency problem in a distributed system is literally just to avoid it. And the sort of simplest idea that sits behind this is the single writer principle. So if I can ensure that all my writes just go into one area and then I effectively have replicas, then at least my sort of consistency, my write consistency concerns can be isolated to a single machine, which makes my problem much easier. And potentially have read consistency concerns over my different replicas, but we'll get to that in a bit. So there are a few kind of names for this, but one term in use is this idea of CQRS, which is command query response segregation. And very simply put, this is just the idea of splitting reads on the, or splitting your writes from your reads. So if I might write some data to this database, and then I might denormalize it or pre-compute a result into something which has a more read-optimized storage engine, and then I can query from that interface. That'll give me a better, or certainly a better response in terms of my ability to write data and my ability to read it. The problem with this, obviously, is that in this architecture, you don't necessarily get to read your own writes, because there's a latency associated with this process here. But the key point here is that the underlying principle of having kind of multiple storage engines within the same architecture is quite a nice one, and it's certainly something worth considering. So if we look at there's a data store, so many data stores actually do something like this, but just as an example, we'll look at Druid. So Druid is a analytics, fairly contemporary analytics engine. Anyone use Druid? No. Yes. No. So this is. I mean, this is a relatively new product. So it just spits out real-time storage from historic storage using effectively different storage engines, like very similar to the ones that we were talking about before. So something that's write optimized for accepting data, and something which is read optimized for providing effectively analytics. And then when it just queries both. So this is all sort of transparent to you, which is quite nice. I still don't know quite how it deals with negation, but I need to look into that more. So the core point, though, is that by using multiple storage engines with a sort of veneer on top, we can kind of get the best of both worlds. So there are other ways that we can take this pattern a little bit further. So this idea of trying to separate the operation of different storage engines within an architecture. So Martin Kleppmann did a very good talk, maybe a year and a half ago, about turning the database inside out. Did anyone ever seen that? A few head nods, yeah. So it's a really nice idea, and that idea is. It plays out for a number of reasons. There's a number of reasons that it plays out quite well. One is that databases are very good at the jobs that they're designed for, but that they have some shortcomings. And one of them is that it's actually quite hard to interact with the database, as in it has sort of fairly set rules in terms of what you can do with it. It's fairly hard to get data in and out as well. So there are some advantages to using an approach which actually explicitly pieces together different pieces of technology to achieve a similar goal. So in this pattern, what we have is a layer which like the Druid example, has the sole responsibility of effectively accepting data and managing consistencies. So that means write consistency. So that's the layer in which we may be transactional. So this is where we'll hold mutable state. Behind that, we have a streaming layer, and from this point onwards, everything is immutable. And immutability is really a really important property in this kind of system, because it allows us to effectively allows us to use replication without having to worry so much about consistency concerns. So we have a mutable layer at the front. We have a stream processing layer in the middle, which clients can potentially listen to, but at the end we'll have a set of views. And the important point here is that those views can be different things. They could be different technologies, or more importantly, they can actually be different cuts of the data. If we want some more data, then we can just replay from our stream and regenerate the additional information that we need. So this is quite a powerful pattern, simply because it's offloading as much of the workload, as much of the analytical workload as we can from the consistency constraints that we would have on a traditional database, and shifting it into an immutable world, which is easier to optimize. The smart people amongst you will notice that time is the tricky thing at that end. Yeah, there are ways around that too. So another sort of similar approach, which really addresses actually quite a fundamentally different problem, but is worth discussing, is the approach used by the Lambda architecture, or this is sort of batch data flow. So typically these will be Hadoop-based systems. Who's familiar with the Lambda architecture? You've got a few. There's definitely a theme. So the Lambda architecture is really just an evolution of the batch data flow pipeline. So when people started using Hadoop, they would generally generate a batch layer, which will iterate through a really just sort of a different set of incarnations of data in some way that's useful, and hopefully come up with some useful results, which they put into a serving layer. And one of the main problems with this, which you may be familiar with even if you've never used Hadoop, because you've put data into a relational database and pulled it out and done something with it and put it back again, and sort of ended up in this pattern of being caught in a persist and query paradigm. These tend to be quite slow. So a chap called Nathan Mars, who wrote Storm, came up with this idea of bolting effectively a streaming layer on the side. And that allows you to get a much faster response to specific workloads, and will effectively give you a fast response, write a result to the serving layer, and then the batch layer will just overwrite it when it's got a sort of spot-on result when it actually gets around to doing it later. So actually, despite this having a name, many companies kind of did this anyway. It's a sort of natural response to the problems that are associated with batch data flow processing. So so this pattern, and I guess the downside of this is you have to have like 2 different layers. Today there are better technologies which allow you to do it in one, but fundamentally you're still separated. It's still sort of separated, so you have analytics working in two different layers. So then there's the idea of the stream data platform. So this is quite a nice idea. This is really an evolution. Oh yeah, I should say that actually. So the big difference between these patterns and this pattern and the previous pattern, or the operational analytic bridge, is that all the data here is just immutable. So we're saying it's immutable by default. And the reason for that is that many data sets that we would use today have no requirement for consistency. As in, if you're collecting logs, if you're creating log files, then a line in a log file never changes. It's immutable by default. But so in the stream data platform, it's a very similar approach to the previous one. The argument is simply that anything that you can do in this layer, or certainly for a large number of use cases, you would be able to do in a stream processing layer, supposing that you have a sufficiently powerful stream processing engine. So this is kind of the same kind of approach, really. We're taking data, we're putting it, but instead of putting it through a batch engine with a sort of a shortcut along the side, we just put it through a scale-out messaging system like Kafka. And then off the back of that, we can use stream processors to create a variety of different views. And the really nice thing about this pattern is that it's sort of a little bit different to the traditional approach of kind of trying to consolidate all your data into one place. Because you can leave state in Kafka, it means you can be a bit more flexible about the way that you create these different views. And actually, the trick to doing this is, as is the trick really with any data-centric system, is to create something where something that has a degree of reproducibility, because it's the reproducibility which allows you to sort of evolve and change things quickly, because data is just really kind of difficult to deal with. So that's kind of that's the idea of stream data platforms, which is quite a nice and powerful idea. And so whilst we can apply that pattern so we're going to apply this pattern to a sort of big data analytics workflow with a sort of powerful stream processing engine like Samza or Storm. we can also use it in sort of bigger data integration approaches. So this is, again, this sort of combination of the last three patterns. So here we just have source systems, which are acting really to encapsulate the consistency concerns within themselves and then stream out a set of immutable changes. And this is something that, in theory, we could have done a long time ago, but actually it's pretty hard to do this in practice. So change capture systems have never really been able to funnel the data, or handle the data flow associated with a large number of databases. But certainly, there's an approach for doing this inside, effectively, a company integration work use case. And then off the back, it's a similar approach again. We can have a Hadoop layer, an analytics engine. We might have something that supports an inverted index, like a search engine. And I guess the other really nice thing about this pattern is this idea of we tend to get caught up in the idea of a persisting state and then processing it. This pattern really just tries to keep data moving all the time. So by keeping data moving by default, then where we want to get to is somewhere where we actually we attempt to process data whilst it's in flight and pass on the result to the next layer, rather than just trying to work out how to persist it so that something else can query it later. And that makes for much sort of more agile and sort of temporally efficient workflows, certainly within both big data pipelines and also within companies. So, things we like. Well, we like treating state as something which is immutable. We like the idea of being able to just append things to a log. That's a nice idea. We like the idea of listening to things that are changing, right? So if we've got a log, then we should just be able to view that as something analytical or something that's just a stream of changes that we want to respond to. And this is something that relational databases have never been so great at. But it's a sort of powerful pattern. The idea of replaying things that have happened before is also quite powerful. The idea that if we have a single sort of chronological stream of state, that we can create something that doesn't have to be all-encompassing from the outset. The idea that we can just create something that's specific to our workload, just the data that we need to solve this problem today. And then when we need a bit more data, when we need some extra columns or to enrich it in some way, we can go back and we can just replay the extra data that we need over the top. That's a really powerful idea for actually getting things done. The idea of trying to split the immutable from the immutable. So we isolate consistency concerns in the smallest possible bound that we can find. That's the best way to scale. And also using both sharding and replication. So replication is actually a very easy way to scale, if you can. If you can just create replicas. So I mean, the key point here is that generally you'll shard at this layer if you need to, and at this layer you'll replicate first and shard later. Okay. And finally, within a single store, we need both of these primitives. So many of the sort of technologies like Mongo and Cassandra to a certain extent give us both of these primitives. But we definitely need both of these primitives. Right? And any solution that doesn't have both of them will be limited, at least in some context. And the final one is being able to reason about time. And this is, as yet, a problem that needs to be solved in a sort of ubiquitous sense. Because as soon as we sit in an asynchronous world, we have to have some mechanism for coordinating. So the way this tends to be dealt with at the moment is generally by either avoiding the problem completely and not talking to different replicas. That's a very simple way of solving the problem. Or the other one is that replicas actually have some context of the time on which they are running, and clients simply have to solve the problem by asking them. And then finally, it's just this idea of basically blending a different set of tools that are right for the job inside a single platform, which allows you to propagate state across it. So that's it. Thank you very much for listening. Are there any questions? I think probably overran slightly, but hey, Dan.
How does DeTomic play into those? From the kind of storage perspective, obviously they've got the time, they've got the single.
They use single writer, yeah.
But do you know how it actually stores it?
So I looked at DeTomic when it first came out, and I haven't looked at it that much since then. So the question was about DeTomic, which is a database which is sort of built in the Clojure ecosystem, really. I thought it just used whichever, well, certainly when I looked at it, it used any pluggable storage engine that you wanted to. I imagine it probably now has one, and I don't know what it is, but certainly when I looked at it, you could put it in anything. People were generally using key value stores. But it may have moved on. It was a few years ago. Good question, though. But yeah, certainly the single writer principle is smart, right? Simple. Simple way to solve the problem. Any other questions?
In your stream-based approach, where you're pushing out to different views.
Yeah.
How have you? I assume the stream is considered to be the source of truth in that structure.
Certainly, yeah. Certainly, conceptually.
In terms of that going back over all time and changing data structures that are going onto that stream, how have you sort of practically gone around managing that?
So you have to. So yeah. That's a really good question. And it's a really good question because the temptation to just update the immutable state in those views is almost overwhelming if you haven't set it up in such a way. And that's why the trick of having it all automated is so important, because you just can't, basically. You have to, in any of these patterns, you have to be able to fix in this layer. Otherwise, this stuff just kind of breaks down. That's in my experience, anyway. I mean, as soon as these start to diverge from the truth, then it just becomes a nightmare. So literally, the trick to this is automation, actually. Like in many problems in technology, it's about having something that you can just click a button and regenerate it. Any other questions? Cool. All right. Well, thanks very much, guys.